All right, so we're going to do some heavy lifting in this video, 3 different topics. All right, the first one is historical. I don't know how many folks actually understand completing the square, how many people can actually draw the pictures. I had to kind of figure that one out for myself. So it might be in the textbooks, I don't know. But what's going on here is mathematicians, x plus 2, x plus 10, this is, a square is not a rectangle that has uneven sides. Okay, so mathematicians figured out that, x squared plus 12x plus 20 equals 5. That's really hard to solve. I mean, you're hoping to get some kind of factoring, x plus 3, x plus 5 gets me 15, for instance, but 3 and 5 don't add up to 12. So is there a way that we can reconfigure this so that we get the same terms, but we are able to solve a problem like that? We are able to solve, well, and what mathematicians came up with is they redrew this area. They made the longer side smaller, and then they tacked on that length to the shorter side, and you got yourself a very new looking picture, except that's not x plus 10 anymore. All right, we want to take off 4 here and add 4 here, so it becomes x plus 6 and x plus 6. Right? 2 plus 10, those are the roots, divided by 2 gets us 6. So that becomes 6 units long. And that means that I can now call this x squared plus 12x plus 36. They're almost equal. They're almost equal, but that's 20 and that's 36. Well, how about I subtract 16? And so what I basically did is renamed x squared plus 12x plus 20. That calculation could have been written as x plus 6 squared minus 16. They're the same calculation. I'll just use one number. Let's use 10, the number 10. Okay, over here, 10 is easy to work with. That's 100, and 120 is 220 plus 20 is 240. If I put a 10 in there and I didn't make a careless error, I'm getting 240. I'm going to put a 10 over here. 10 plus 6 squared. That's 16 squared. I think that's 256. Oh yeah, 256 minus 16, 240. They're the same calculation. Now, what's the major difference? The major difference is the variable only appears once on the right, appears twice on the left. Huh. I can't use inverse operations over here. I can't use inverse operations. It's not written as a function of x. This is. So when I set this equal to 5, look at the ease in which I can solve this. X plus 6 squared equals 21. X plus 6 equals plus or minus the square root of 21. Therefore, my roots are -6 plus or minus the square root of 21. I didn't have to think too hard. Hope you saw all that. Yeah. All right, so that's what the history is behind completing the square. And this is beneficial here. That's really beneficial because you can see your vertex, -6 minus 16. Now, how do you know that's your vertex? Because there is a smallest area. Oh, I can draw a smaller square, excuse me. Oh, I can draw a smaller square, excuse me. Oh, I can draw a smaller square, excuse me. So what's the area of a smallest square? Right, because that's the squaring process, right? 1, 1, 2, 4, 3, 9, it's got acceleration. The smallest is when you get this. When do I get that for this? Obviously, when x is -6. So that's kind of how you can spot the vertex. And that's enough on that problem. I just want to give you a taste for what the heck, where'd that phrase completing the square come from? It came from that process. Yeah. All right, so now we're going to do exponentials. All right, yesterday we did the Newton's law of cooling, the coffee. Now we're going to do Newton's law of warming up. I'm putting a pizza in the oven. I'm going to do 3 or 4 of these. You're not going to see this one again, I don't think. Okay, it's just the thought process. I want to analyze the thought process. Okay, we're going to be dealing with growth and decay functions. That's what people work with. Okay, they don't work with pizza in the oven, but you could. So temperature of the pizza based on minutes in the oven. Okay, what's the most important temperature in this problem? It's the oven. You don't want to be in there. Yeah, no. Okay, so 350 is the most important temperature. I'll put the degree symbols there. All right, and then we want to look at, that's my first temperature on the left side. It's easier to write these equations left to right. We can write them right to left. I might do that for you after midterm. It does help us a little bit understand exponents, but right now I'm at 32. So the question is, how much does this pizza have to warm up to get to the oven temperature? 30 makes that 320, 318. So I am 318 degrees of warming has to happen in order to get this pizza 350 degrees. That's why you don't bite into a fresh pizza after it's been in the oven a while. You got to let that cheese cool down because underneath it's really hot. You'll burn your mouth. I'm trying to help you here. All right, so 318. I guess I got to go down 318 degrees in order to get to that temperature. The next time I don't have to go down that much. The next time, you know, I'm going to do a different calculation. So I'm going to put that here because then the next time I don't have to worry about the 318 because I want to get from 350 to 290. That was an easier subtraction. I want to go down 60 degrees. And if I divide degrees into degrees, those actually cancel and I get a generic number there. It's not even in degrees anymore. It's just some number. Okay, so what I basically did is I used these numbers already, so I don't look at them again. I turn my attention to the minutes. Well, 0. You know, something to the 0 seems really easy for me now. We talked about that. It doesn't matter what's in here. Right, you can have a J over a B. To the 0 is 1. Okay, so it doesn't even matter what you put in there. It's a 1. So that's nice. I like that. So I'm going to make this a 0. Oh, it already is a 0, but I'll write t minus 0. Just because lots of times I give you a different number. And how far is it from 0 to 15? 15 minutes. If you put that equation into Desmos, you'll get this graph. You'll get this graph because this is a fraction less than 1. Right? It looks like it's close to a fifth, a sixth. You know, if you multiply some quantity by a fifth, well, then really you're taking everything away except a fifth. You're leaving just a fifth of whatever you started with. And if you do it again, well, then a fifth of that is that. And if you do it again, well, I hope you see that this is decaying. Right? This whole number, whatever it is, that number, a fifth of that number, and doing it again every 15 minutes, a fifth, a fifth, a fifth. It disappears pretty quickly, leaving you heading to 350. That's why we have what's called asymptotic behavior, which should not, what was it? This should not be confused with isotopic behavior. I had a freshman call it isotopic behavior. So no, asymptotic behavior means that one of your values, either the X or the Y, is starting to become patternable. 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 Okay, it's very patternable. Every one of those Y's is pretty damn close to 350. Darn close, excuse my French. Okay, and that's how you write exponential functions. So let's just put a 0 in. 0 divided by any number is 0. Anything that the 0 is 1. 350 minus 318 gets me 32. Let's put a 15 in. 15 divided by 15 is 1, which means I get this fraction, which means the 318s cancel. And I get 350 minus, well, they don't cancel completely. It gets to be -1. -1 times 60 is -60. So 350 minus 60 gets me 290. Okay, so now we're going to do the ones that are just growth and decay. We'll do 2 or 3 in a row real quick. You can pause the video, take more time. I got to finish before my next class. which is in about 20 minutes. And I got one more topic over here. Don't know how long it's going to take. So I'm just going to put some problems on the board. I'll do them really quickly, and then you can practice 4 or 5 and just pause. So let's say y is 10. Let's do an exponential growth. Let's say that you've got 4 gets you 18, and a 20 gets you 53. Okay, I'm not thinking about easy problems. I'm just going to do the answer. You pause and try. So y equals 10 plus 8. Next one's not 8. 10 to 53 is 43. So it's exponential growth. T minus 4 over 4 to 20, 16. Okay, now I'm going to do another one. I'll do exponential decay this time. Boom, boom. Okay, so let's do y equals -5. Let's go -3 gets you 17. Is that above -5? Yes, it is. Lots of way. All right, and then let's go over here to 23. We'll do that. That'll be nice, I think. 23, and that gets me maybe, how about -2? Okay, so what's this answer? Well, I know all of my values are above -5. So I know I got to go above. Okay, how much above is -5 to 17? 22 units. So the next one's not going to be 22. The next one's going to be, how far is it from -5 to -2? 3 units. All right, so I want a -3 to act like exponent of 0. So I write that, and -3 to 23 is 26 units. Okay, do a couple more. You pause the video. Try to correct your mistakes. Try to learn how to do it, because we're going to morph these things into something else. Oh, let's graph one. Let's graph y equals 5, 2 to the x minus 3 over 4 plus 7. Let's graph one. Okay, y see 7. Boom, 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 boom. Y equals 7. I see that if I put a 3 in, I get the initial amount plus 7, which is 12. So 3 gets me 12. I'll put that here. Okay, 3 gets me 12. Then I know the next time I'm going to get 17 out of this. 17 is bigger. The question is, what is the value that's going to get it? Let me put 312 over here just so that you get a clearer picture. 312. I know I'm going to get 17. That's going to be when this changes by, so 7 gets you 17. And 3 gets you 12. Okay. Okay, let's find out. 3 minus 3 is 0. 2 to the 0 is 1. 1 times 5 is 5 plus 7 is 12. 3 gets you 12. Let's put 7 in. 7 minus 3 is 4. 4 divided by 4 is 1. Oh yeah, I get 10 plus 7, 17. All right, so now let's use the picture and go back to the equation. Oh, well, I see 7. How do I get to 12? I got to add 5. The next time I don't add 5. No, from 7 to 17 is 10. And that's going to be t minus 3 over 4. Oh yeah, that's where that 2 came from. That's where that 2 came from. Yeah. All right, let's try another one. Boom, 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 boom. Then I'm going to go with the sinusoid. Let's go y equals 8. Let's get exponential growth was the last one. Let's do decay again. Let's call this -4. Let's go up to 100. Let's go down here to 660. Let's call that, let's use some numbers, because exponential functions usually go with numbers. So there's always been 8 sheep in gill. In 1953, there were actually 20 sheep in gill. And in 2004, there were actually, I don't know, 10. I don't know, that can't be 10. Yeah, it can be close to 10. Yeah, 10 sheep. All right, so what's the equation? The sheep population has always been bigger than 8. How much bigger than 8? Well, if I go to 20, that's 12 more sheep. The next one's not 12 more. Oh, the sheep population is decreasing. Poor sheep. The next one, 8 to 10, is 2. Oh my God, 1/6 of the sheep population. This pandemic is scary. T minus 1953 over 1953 to 2004 is 51 years. Okay, you put that in Desmos, you've got this graph, then you got lots of help, lots of computer help. Okay, sinusoids. 15-minute discussion of sinusoids. I hope I remember the time my class starts. Oh my God, I should check it, but I'm afraid to. I'm afraid to. Oh, my goodness gracious. Oh, I'll do a separate video. I got to check it. So I'm going to do 2 videos. Bye-bye.